Okay, so this whole video, and I think some videos after this, if I cannot complete this video at one go, they will be about understanding binomial theorem from the basics. So this will be more involving. I mean, it's gonna involve more explaining and less problem solving. Because well, somebody asked me to uh, to basically explain the theory of binomial theorem and how we can uh, how we can solve the series that contain binomial coefficients and stuff, right? So that's why I think it's better to just start from the basics. So this is the binomial theorem module from ACE, and I mean honestly, when I first read this, it was, I think, pretty self-explanatory, except I already knew how binomial theorem actually works. So maybe I didn't see what difficulties one could experience, right? But anyway, so first of all, we'll start with what the binomial coefficient really is. So we start off with NCM, where n is bigger than m. This is the binomial coefficient. This is sometimes also written as n, m, and brackets like these. I like this thing because this looks somewhat like a fraction, so I avoid this. Right, what does this mean? This means the number of ways of choosing m elements out of n distinct elements. And when I say choose, I mean you want to form a set of these m elements such that there will be no ordering of this set. So this is a special case of the multinomial theorem. So how does the multinomial coefficient? So what's the multinomial coefficient, you might ask? So say you have 6 distinct objects and you want to make I don't know, 3 sets of, let's say, 2 2 2 out of these 6 objects, right? So you have I don't know, call this in 1 2 3 4 5 6. So I'll just label it like that. So maybe these are 6 different color balls or something, and you want to put them into 3 sets. Now each of these sets will be distinct, right? That is, so that means even if I somehow get the same kind of configuration, just the sets that I put it in are different, right? It's still considered a different configuration, right? So for example, this set 1 2 3 4, so this kind of distribution, right? You have this kind of thing. This will be considered distinct from this. So you just got 1 2, and this is now 5 6 and 3 4, right? So both of these will be distinct. Hope that makes sense. Okay, so now how do we do this? Well, first of all, what we'll do is that we'll just arrange these. So the ordering of these things, we'll just arrange that order, and the number of ways to do that is just 6 factorial. Now how I should explain that, but I think that's pretty basic, but still let's explain this. So for the first place, so while we are ordering this, right, I mean, we are just setting the order right now, and we'll just put the first 2 elements into this thing, and the next 2 elements into this, and the next 2 elements into this, right? So just order and just push these into these containers, right? So the ways to do that, the ways to order this, that would be 6 factorial, which is just 6 into 5 into 4 into, yeah, so on. You get the idea. Now why that? So for the first place, you have 6 choices, so that's why 6 ways of doing this. And then for each of those ways, for the second place, you can have 5 choices because you already used one of those. And then the next place will have 4 choices for each of the distributions of these first 2 places, right? And then it keeps on going. So eventually you'll just get 6 factorial. Yes. And now once you have done that, you will just push these into these 3 sets, right? And then you might say we are done, right? So 6 factorial is the number of ways to do that. But you will be very wrong by saying that, because if I say have this kind of configuration, so it's all of these are the same, but you just switched 1 and 2. So pushing this kind of distribution into these three sets and pushing this distribution into these three sets, both will give us the same thing, because it doesn't matter if it's 1 2 or if it's 2 1, because it's a set, it's not an ordered list, right? It's not, the order doesn't matter. So we have to divide by 2 factorial, because you have 2 factorial ways of arranging this same thing into that, and then each of these ways, right, those will also, so basically what we are saying is that whatever the original number of ways is, the true number of ways, that times 2 factorial cube. Now why cube? Because there are 3 of these, so it's better if I write it like this: 2 factorial, 2 factorial, 2 factorial. So 2 factorial because of this, right? So whatever the original number of ways are, you could just take one distribution from that n, right? And then you could start switching this and switching that. Well, if this was like 3 elements over here, you would have 3 factorial ways of switching and arranging in this set itself, right? And each of these will give some distinct class of orders. And then you could switch this as well, so another 2 factorial, and then once again another 2 factorial. So that will be number of ways to have an ordered list of all of these, right? So going from left to right, that is that kind of list. And we know what's the number of ways of finding that list, right? Which is just 6 factorial, and that's why n is equal to 6 factorial upon 2 factorial cube. Now if this was something else, if you had, I don't know, 3 elements for the middle thing and then just 1 element for this guy, right, then this would be 6 factorial upon 2 factorial, 3 factorial, 1 factorial, because now this number will be 2 factorial. And then for this guy switching these 3 elements in this set alone, you would have 3 factorial, and then there's just one of these, so 1 factorial. And that's why n will be 6 factorial upon 2 factorial, 3 factorial, 1 factorial, right? Now this is the general multinomial coefficient, which is also useful, but what we are looking for right now is just the binomial coefficient. That's the special case of this, where there are only 2 sets, and because there's only 2 sets, you can in fact even get rid of the other set by considering this question of selecting some m elements out of the total n elements, right? So when you select those m elements, you are automatically deselecting the other m elements, so you are basically partitioning this into 2 different sets by itself, right? So this question and partitioning to 2 different sets is the same thing. Similarly, if you wanted to select 2 sets of, let's say, p and q elements, then you would in fact be partitioning into 3 sets of p, q, and n minus p minus q, right? So going with the same logic, this thing will just become n factorial upon m factorial times n minus m factorial. So the set that we have to deselect, right, that guy's order also doesn't matter, and that's why we have to divide by this thing. So this will be the total number of ways to select m objects out of n objects, right? Hopefully that makes sense. So now that we know what the binomial coefficient is and why it works the way it works, let's actually go to the binomial theorem. Okay, so the way this is normally given in textbooks is as you can see, so it's just like a rule. I mean, they just tell you how to do this. They don't kind of give you the proof, but okay, they gave us a proof, but yeah, you can see like this is not very readable. So I'm going to provide, I think, a better explanation. So what I call a better explanation, at least the one that made the most sense to me when I was learning this. So let's start with simple cases. Let's start with x plus y to the power of, I don't know, 1. It's just going to be x plus y, right? Then x plus y to the power of 2. This thing is just multiplying this thing by x plus y, right? Yes. So yeah, and the way to do that is first of all multiply by x. So x squared plus xy, and then multiply by y. So yx plus y squared, and I am intentionally writing this as yx and not xy, because that represents the order of the multiplication. So how we multiplied. So for example, if somehow multiplication was not commutative, then you would have to write it as yx, right? So that will be this thing, x plus y squared. And then if you want to do x plus y cubed, we'll just multiply this by x plus y. So basically you are applying x plus y on this thing. So something like that, right? Yes. So how will that be? Just multiply everything by x. Yes. So it's going to be x cubed plus, maybe I should just say x and plus x y and then plus x y x. So instead of writing x cubed, which is, yeah, I mean, you can write this x cubed, but to actually understand why the binomial theorem works, maybe it's better to write it like that. And then plus x y y, and then you have y doing the same thing, so like y x x plus y x y plus y y x, then plus y y y. So now notice this thing, every single term from here is basically made by taking either x or y from each of these multiplications that we did. What do I mean by that? So x plus y cube is just x plus y into x plus y into x plus y, right? Now to get x plus y squared, what you had to do is you had to multiply this thing by first x and then y. So while doing that, what you are actually doing is that you are taking either x or y from this bracket, right? Specifically it's like x plus y times x plus y. So you are either taking x or y from this bracket, and then you are multiplying this by either x or y from that bracket, and that generates a term, right? So does that make sense? I think it should. So that generates a term. For example, if I take x and then I take y from here, it will be yx. So not xy, yx. And then if I take y from here and x from here, it will be xy, and so on, right? So yeah, like each of these terms from every single bracket, you have to take just one term from each single bracket while generating these terms, right? Because that's the way multiplication is going to happen in the whole process, right? Think about it. Just think about it. This originally contains these kind of orders where you consider one term from here, one term from here. So right, that thing. And then you multiply this whole thing by x plus y to get x plus y cube. So you are either multiplying by x, right? You're adding an x on the left side of each term, or you're adding an y, right? And that's why it's either x or y from the next bracket. So this third bracket, you will just put that thing on each of these, and all of these will in fact, I mean, some of these will not be distinct if you consider a multiplication to be commutative, right? But if it's not commutative, all of these will be distinct, right? Yes, because this thing can either be x or y. Yes, and that kind of fixes what the number should be, because if this is x or y and this is x or y and this is x or y, so you can think of it as binary. So if you have any experience of writing numbers in binary, how do we do it? It's just like 101 or 010 or 110. So like, yeah, you write out the binary representation, and every single representation is unique, right? All of these represent different numbers, something like that. So all of these sequences, they represent the different terms, and each of these terms that we obtain by this method of considering one term from each of these brackets, right? All of these things, they will be distinct, right? You cannot have the same thing from the same ordered list or ordered sequence from doing this two different times in two different ways. You cannot have the same thing, right? It's just not possible, because the sequence will be different, or the contents are different, or something like that. So, well, that's good, right? So now the question is, how do we figure out the coefficient of x squared y considering multiplication to be commutative from this kind of expansion? That will simply be the number of times a term that contains 2x and 1y comes. Now each of these sequences, it's just made from considering one term from each of these brackets, right? So this question is basically like asking, what is the number of ways that you can select 2x, so two brackets that will produce an x in the sequence, and one bracket that will produce a y. And we know the number of ways of doing that. That will just be 3c2, right? Basically like 3 factorial upon 2 factorial 1 factorial. So yeah, because 2x and 1y brackets, right? So two brackets that give us x, one that gives us a y. Each of these brackets is kind of distinct, and there are 3 brackets in total. So that's why 3c2, right? And of course, I mean 3c2 is just 3 into 2, so like 3 factorial upon 2 factorial 1 factorial, that will just be equal to 3 into 2 into 1 upon 2 into 1 into 1. So this will just be 3, and that is exactly the coefficient of x squared y in this expansion, right? It's just going to be x squared, x cubed plus 3x squared y plus 3xy squared plus y cubed. So that works out. Yes, I mean that should make sense. And then of course this is linked to the Pascal's triangle, right? So the way that happens is that you whatever you have over here, just multiply that by x. So if this is like x squared plus 2xy plus y squared, multiply by that by x, and then you just write it to the left a little. So x cubed plus 2x squared y plus xy squared, and then you multiply by y. So you write it just down of it, but skipping one term. So that will be x squared y plus 2xy squared plus y cubed. And now you can see when you add these up, like these two pair up. So this is the 2 from here, and this is the 1 from here. So 2 plus 1, 3, right? And that's why the Pascal's triangle thing also, in fact, just has binomial coefficients in its entries, right? So now that I've given you the idea of why binomial theorem actually works, let's go to the actual proof that they gave us. And of course, this is just for natural number of indices, right? So the index must be a natural number. Otherwise, combinatorically, we cannot prove that the binomial theorem works the way it does, right? So there are multiple ways of doing this. You could use Taylor series and all kinds of things to prove that the binomial theorem will work. So that's something that you will need to do while proving general binomial theorem, because that does not make any sense combinatorically, right? But for the normal binomial theorem, which has integer powers, right? You can do this just by counting. So this is nice. Let's just delete off. Or let's just go to the next page. Whatever. Okay, now let's read the proof that they gave us. So binomial theorem for a positive integral index. If n is a positive integer, then a plus x power n is given like that. Yeah, that makes sense, of course. Yeah, so you got x power 0 and nc 0, and then a power n, and then nc 1, x power 1. This is 1. It's not written, but it's supposed to be 1 there. And then a power n minus 1. So you increment x's power by 1, and a's power you decrement by 1. And then keep on going. And then you change this binomial coefficient from 0 to 1, and then 1 to 2 and 3 and so on. And it keeps on going. And then midway you have some generic term. So NCR, where R is just any number which is less than or equal to n, bigger than or equal to 0. So NCR, x power n minus r, a power r. Okay, they should not have written it like that. They should have written it as NCR x power r and then a power minus r, because that's the way the series is going. But fine. The thing is, like NC n minus r and a power of r and x power n minus r, this term will also be there. And what happens is that these two coefficients are the same, because this thing is just n factorial upon r factorial n minus r factorial, and this thing is n factorial upon n minus r factorial. And then what's n minus of n minus r is just r, so r factorial. So these two are identical, and that's why they can write it like that. But it's not correct to write it like that in this kind of series, because you can see r is like increasing. And yeah, so over here, whatever number you have the same number as the power of x. So this representation is like better, I think. Anyway, so that's the binomial theorem, what it actually says. Oh yeah, and NC0 is, so 0 factorial is 1, from that it follows. Fine. So yeah, the two different representations of binomial coefficient. Of course, of course. So at first, it looks like, what is this? This is so huge, and we cannot, I mean, possibly remember this. But then you get used to it, because this really is, I mean, they just wrote it in a very ugly way. They just write it in a proper, understandable way. So this will be a summation. Is the sum as r goes from 0 to n. So the last term is n, right? And then it's going to be a power r minus n x power r, but that all of that times some extra number, which is the binomial coefficient, so ncr, right? So this thing is just equal to a plus x to the power of n. So this sum is equal to a plus x power n. Now this kind of, I mean, expansion, it has like very it is very important, because it shows up everywhere, right? So in derivatives, I mean, while proving derivatives and everything, it shows up. It shows up using by using generating functions and whatnot. And yeah, so this has tremendous importance. Anyway, so they also gave us a proof. So by induction, I'm just gonna skip over it. If you can read if you want, because I think I proved it good enough. Oh, whatever, I'll just prove it their way. So they are saying a plus x power n is equal to nc0 a sub a power n x power 0 and so on, right? This series. So they are saying, let's check if p n plus 1 also works. That is a plus x power n plus 1. Will this also be given by a similar expansion, right? So yeah, I mean, they are just taking a plus x power n, writing it out by the assumption that it works till n at least, and then we are multiplying by a plus x again on both sides, and then I mean, expanding the thing, right, distributing a and x, and then writing out the series once again. And yeah, it works out, of course. So let's see what they did. Okay, whatever. So where's the main step, the proper induction step, right? M plus 1. So a plus x power n into, come on, they, okay, whatever. I mean, they had to use m over here, not n. I don't know why they switched this, but it's supposed to be m over here. So p m plus 1, that's the, if the statement works in m plus 1 as the index, right? That's what they're checking right here. So don't get frightened by whatever this symbol means, right? Just ignore that. We're just looking for a plus x power m plus 1, right? So they do this thing, they multiply this whole polynomial by a plus x, and then they write it out. They write this to the left a bit, and then this to the right a bit, the same way that I did for x plus y. So, right, basically like Pascal's triangle, right? Something like that. And then they add this up. So yeah, and then MC1 plus MC0, MC2 plus MC1, and so on. So it just so happens, or in fact, it's not like it just happens. It's not a coincidence. It's going to happen because that's the way it is. So it happens that NCR plus NCR plus 1 is equal to N plus 1 CR plus 1. So there's also another very nice way of proving this little thing. So this is called Pascal's identity. And yeah, I mean, this is really important because this can help you write out N plus 1 CR plus 1 as a series, and you can do all sorts of crazy stuff with it. But what it's basically saying is that the number of ways of choosing r plus 1 people out of n plus 1 people is the same as the number of ways of choosing r out of n and r plus 1 out of n, those combined. So let's prove this combinatorically first, and then we'll give it an algebraic proof as well. So this is like a really important property of the binomial coefficient. Okay, because this is going to be used in questions most likely. Okay, so let's give a proper combinatoric proof for this. So you have n plus 1 objects, and out of these you want to choose r plus 1 objects. So let's just consider the first object. you could either have the first object in your selection, and now if you have done that, your whole task is just reduced to choosing r objects out of n objects. So just draw that out. So you have maybe, I don't know, n plus 1 cubes. It's like numbered. It's 1 2 3 4 5 6. So for now, just say n plus 1 is 8. So n would be 7. So out of these, first of all, let's just consider one single object, and let's see what happens if you take that into selection and if you don't take that into selection. So if you take this object, so the 8th object into the selection, right? So if you select that, then your whole job is reduced. So I don't know, let's just say r is, I don't know, 5. So you want to have yeah, r is equal to 5, so r plus 1 will be 6. So what we are looking for is 8c 6, right? So out of these 8 objects, you want to choose 6 objects. So you could either choose this, so then you just have 7 objects left, and now since you have chose this thing, you just need to choose 5 more, and that's why it's going to be 7c5. Or you could not choose this, so you still have just 7 left, but now you have to choose 6 objects, not 5 objects, because yeah, this is not selected, so there are still 6 objects that you have selected. So that's why 7c6. And then the general statement would be this thing: n plus 1 cr plus 1 is equal to ncr plus ncr plus 1, right? That makes sense. And also let's just prove this, algebraically. So n plus 1 factorial upon r plus 1 factorial, and then you got n plus 1 minus r plus 1, which is just n minus r, that thing, okay, factorial. Is this equal to ncr, which is n factorial upon, well, r factorial, and then you got n minus r factorial, plus ncr plus 1, which is just n factorial upon r plus 1 factorial, and then you got this thing, n minus of r plus 1, so n minus r minus 1. I'm just getting out of space. So this other thing is going to be n factorial upon r factorial, and then you got n minus r minus 1 factorial, right? So sorry, it's supposed to be r. Is this thing true? First of all, n plus 1 factorial is just n plus 1 into n factorial, which is like obvious. So you can get rid of this thing altogether. Okay, next, you know that n minus r factorial is just n minus r times n minus r minus 1 factorial. So this is like obvious. I mean, for every number, say k factorial is just k times of k minus 1 factorial, right? Because this is k into k minus 1, so on, and which is just, I mean, like k into k minus 1, so on. That makes sense, right? And that's why you can cancel this away and cancel these factorials, right? So this is the thing. And now once again, r plus 1 factorial is just r plus 1 times r factorial, so you can cancel this factorial away and cancel these terms out. Yeah, that should make sense. So this just becomes n plus 1 upon r plus 1 times n minus r. Is this equal to 1 upon n minus r plus, that's just 1, I think. No, that can't be. This is r plus 1 factorial. So there's no r factorial right there. I mean, that's gone, right? There as well, you just have oh, it should be r plus, sorry, it should be r plus 1 there. Why did I, it has r factorial? So originally it was just r plus 1 factorial, and then you divide by r factorial, so you get rid of that thing, and that's why it's going to be r plus 1. So this is just 1 upon r plus 1, and then yeah, it's just cross multiplication. Do this thing, just get n plus 1 on the top, so n minus r plus 1. That's why n plus 1 upon n minus r into r plus 1. So yeah, exactly this thing. So algebraically as well, this makes perfect sense. But I still like the combinatorial proof better because it's more intuitive. Yeah. But just let me give a warning. Just because something is more intuitive does not mean that it is correct all of the time. So it was important for us to prove this algebraically as well. Okay, second proof. That kind of proof that I like. So yeah. a power nx product, now taking a n minus 1 times nx once we get, yeah, exactly. So this is the proof that I was talking about at the first page, right? This whole thing. Yes. So I like this proof much better. Anyway, so you can read all of this. Okay. Similarly, yeah, let's exponent is equal to, okay, whatever. Oh yeah, so minus x. We already proved that a plus x power n is equal to summation of from r is equal to 0 to n of ncr x power r and then a power n minus r. So instead of x, you can put negative x in there, right? So x is like any number, real number, imaginary number, doesn't matter. Put anything in there. So you might as well just replace it by negative x because that's also allowed. So a minus x power n is equal to summation from r is equal to 0 to n ncr negative 1 power r x power r a power minus 1, sorry, n minus r. So negative x power r, which is negative 1 power r times x power r. So that just makes it an alternating series. So r equal to 0, this thing is 1, r equal to 1, this will be negative, and so on. Sorry. Okay, so that's nice. And then you have a plus x power n plus a plus x, so a minus x power n is equal to. So we won't be using this right away. We will use this for each special case individually, right? Let's not, I mean, this dot, you don't know where it stops. So when you have been given numbers to feed in here, you will know where it stops, right? But yeah, this is how it is. You just add these up. So for even numbers, you don't have that cancellation happening. So 1 plus negative 1 power r, that becomes 2 instead of becoming 0. For odd numbers, it becomes 0. So that's why that's what they wrote, a plus x power n plus a minus x power n is equal to, so basically like 1 plus negative 1 power n or whatever. So only for even number it survives. So for even number it's going to be 2. So 2r is even, and then we don't know where it it's supposed to be n. We don't know where it stops because n may be even or odd, but yeah, it starts from even numbers. So sorry, it only starts from even numbers, and it obviously starts from 0. Yeah, and it's just going to be ncr x power r a power n minus r, right? They should do it, and then that's exactly what this sum is. So this is one of those times where writing it explicitly and not like this is actually better. Yeah, that's what this is going to be. And then similarly for subtraction, so for all the even numbers it will cancel away because 1 minus 1 is 0. But for odd numbers it's going to be 1 minus of minus 1, which is 2. So this will be n being odd. So if this was negative, this will be n being odd, and then the same thing, right? Okay, so we got this. Properties of binomial expansion, number of terms in the expansion of a plus x power n is n. Come on, it's obvious. It goes from 0 to n. So 1 to n, that's n numbers. 0 to n is n plus 1. Yeah, right, whatever. Binomial expansion is homogeneous expansion. I mean, that's obvious, right? So from this proof alone, you can see why this is the case. And also, like from dimensional analysis, for this sum to make sense, if x and y are not unitless, these can be having units. All right, these can be having units. So yeah, if x and y are not unitless, then x and y must have the same dimensions. So yes, and then when you expand this, whatever this expansion is, all of the terms over here must have the same expansion. So since x and y have the same expansion, these must have the same quote unquote degree. So over here, degree just means the power of x and power of y added up, right? All of this must have the same degree. Okay. So I hate dimensional analysis in maths because it's unnecessary. But yes, sometimes it gives more clarity. But anyway, in physics, it's very much appreciated. Okay. So homogeneous expression, got it. General term, yeah, I mean, we have been summing that all of this time. odd terms have even binomial coefficients and even terms have odd binomial. What do you mean by that? So, uh, what do they mean by even binomial coefficients? Do they mean the binomial coefficient's value is even or that R value is even? Which is probably what they mean, because yeah, it's not necessary that it will be even all the time, is it? Actually, it is. Yeah. The thing is, if you look at the Pascal's triangle, right? This will actually turn out to be even, right? Right. So if you look at it, 1, 1, 1, 2, 1, 1, 3, 3, 1. Look at this. The first term is odd. The okay, no, this got disproved really fast. Yeah. Uh, so for example, x is equal to 1, right? You can see the even term, the second term, right? That's odd for some reason. Yeah, and here as well, the third term. Okay, so sorry, the second term over here. This is the wait. They said that odd terms have even binomial. So this term is odd. This term is odd. Both of these have odd binomial coefficient. So this is not what they mean. Okay, what they mean is that t sub 1 will have the binomial coefficient as nc0, not nc1. So this is just notation, right? That is, whenever r is equal to 0, you will say it's the first term. Whenever r is equal to 5, you will say it's the sixth term, and so on. So for ncr containing terms, it will be the r plus 1th term, right? And then this is pretty obvious. I just proved this right now. Yeah, r plus 1 term from the end is this. Okay, whatever. Not interested in this thing. N minus l plus 1 minus r plus 1. Okay, whatever. So yeah, I mean, this is not just for the binomial series. You can use this for anything actually. So you have terms labeled as 1, 2, 3, 4, so on, and then it's gonna stop at n, right? And then you're talking about the r plus 1th term from end. Yeah. So the thing is, you are replacing n by 1 and n minus 1 by 2 and so on, right? So number of jumps that you will have to make, what will those be? R jumps, right? Because so for example, going from 1 till the r plus 1th term, you have to make 1 to r plus 1 r jumps, right? Because every jump increases your label by 1. In this case, it decreases by 1, but you get the idea. So you have to make just r jumps, and that's why n minus r. And that's what. Oh, okay. So this is from the end is this term from the beginning. Oh yeah, I mean, the thing is, this is n plus 1. Sorry, this is like n plus 1 minus 1, and that's why actually it should be n plus 1 minus r for this particular case. But generally we go till nth term. In this case, we're going to n plus 1th term, but generally we go till nth term, and that's why it's going to be n minus r simply. So the r plus 1th term from the end is just the n minus r term from the beginning. So it's just the yeah, it's doable. So for general series, that's the way it is. But here n has a different meaning. It's not a number of terms. Number of terms is n plus 1. So that's why this thing plus 1. Yeah. Okay. Now they have given us some kind of example. 2x upon 3 minus 3 upon 2x power 6. Yeah, you could do that. Sure. So it's a lot of calculation, really. I mean, no, this is just, why would somebody want to do this? Calculate like 7 terms individually, and then why? It's just so unnecessary. Yeah, it's just so unnecessary. Okay, whatever. Express this thing as a polynomial in x. Oh yeah, so this thing right, so the thing is that all of these odd terms, they will get cancelled up, as we saw previously, and that's why all of these terms which contain square root of x plus 1, x squared plus 1 to some odd power, those will get cancelled. So only the even power containing terms will be there. And even power of square root, it's gonna be x squared plus 1 to the some integer power, right? And that's why it will be a polynomial. So yeah, just calculate this and then you can do it, right? So this is using that formula that they gave us. Where did it go? Right, this thing. So no problem, you can do it. It's just calculation at this point. It's not really maths. The fourth term in this expansion is 5 upon 2 for all x belonging to real. What do you want to find? I think they want to find m or p or whatever. Okay, so they have this thing. Okay, since the term can be seen is independent of x. Oh, okay, I understand what's happening. So it's gonna like split exactly in half and half. So this will be m upon 2 and m upon 2. So the fourth term, that's like the r is equal to 3 terms. So this will be x cubed and the 1 upon x cubed. So m should be 6. That's, I mean, you didn't have to do all of this. Come on. M is equal to 6, of course. That's independent of x. And then once you know that, you can figure out what p should be to get that thing. Yes, just find out a term, put this value in front of it, and then solve for p. So yes, find the value of a and n. Right, so it's gonna be like this. These kind of questions. So till now they don't involve series or anything. Okay, so let's just skip all of this and go to the first exercise. Okay, in the expansion of, so in chapter 1, let's go and do it. In the expansion of x plus a power n, if the sum of odd terms be p and sum of even terms be q, prove that p squared minus q squared is equal to x squared minus a squared power of n. Okay, sum of odd terms is p and sum of, oh, so this is not that bad. The whole thing is that if you want only the odd terms, what you can do is just put x is equal to 1 in there. So it's like 1 plus a power n, subtract by putting negative 1 there. So it's going to be a minus 1 power n. And then divide by 2. That's going to be the sum of the first, sum of all the odd terms, that is. Right? So it's it goes from that formula that we have. So x plus a power n minus a minus x power n, so n. That's supposed to be equal to 2 times summation where r is odd of ncr and then x power r, a power n minus r, whatever. The thing is, ncr, a power n minus r, that as a whole is considered the coefficient, not just ncr, right? And then you got x power r or whatever. So just putting x is equal to 1 into this, you can see that you only get these coefficients. You don't get x over here. And that's why you can do that, right? That would be the easiest way to do it. So it's basically saying a plus 1 power n minus a minus 1 power n upon 2. That's the sum of the first odd terms. That is p. And a plus 1 power n plus a minus 1 power n upon 2. That is q, right? So just go and see the formula once again. This is pretty obvious. Okay, so of the even terms be q. Prove that. So first you have to prove that p squared minus q squared is x squared minus a squared to the power of n. Wait, what? Oh, so they okay, they want the term itself. Oh, sorry, I misunderstood this. They don't want the coefficient. They just want the terms. Ah, you have to put that x plus. Okay, this is really bad. So just put x in there. Sorry. First question had to feel so hard. Anyway, this is what they're talking about. So they have to, so we want to prove that p squared minus q squared, so this thing squared minus this thing squared is x squared minus a squared to the power of n. How hard can this be? So it's just going to be, wait, what? But it's got positive and let's see what this gives us. Right, so it's going to be negative. So we got 4 over here, whatever. So it's got negative 4 because minus 2 is minus 4, and then we got a plus x power n times a minus x power n. Yeah. Right, that's p square minus q square most likely. Plus negative 2, and yes, it should work. This cancels, just get this thing as, yeah, it's going to be negative of a square minus x squared over n. Now, this is, I mean, why? It only happens when n is odd, right? Yeah, it only happens when n is odd. This shouldn't happen normally. Huh? Even terms pq. Oh, okay. So when they said odd terms, they don't mean odd coefficient terms, right? So r is not odd. Instead, the label of that term. So which term is it in the sequence? So the r is equal to 0 term is first term and so on, right? That's what they mean. Okay, then just switch q and p in that case. So then this makes sense that it should be positive. Yeah, fine. So then this makes sense. And then, oh yeah, of course. So yeah, I guess it makes sense. It's got a plus x power n plus all that stuff, and then it got 2 times of that. Wait, it should be a squared minus x squared. Why is this? Huh, this is weird. Oh, you could write this as p minus q into p plus q as well. Yeah, that's one thing you could do. So p minus q, that will just give us a minus x power n, and then p plus q will just give us a minus x power a plus x power n. So this should in the end just be a square minus x square power n. I don't see why this should be x square minus a square. It should be a square minus x square, right? It should be opposite. Why is this here? Yeah. Oh, okay. Ah, man, these people are just so fine, fine, fine. Now I understand what they really want. So this is not supposed to be a polynomial in x. It's instead supposed to be just the expansion as seen. They are not. This whole terminology. Okay, now I understand what's happening. So it's not supposed to be a minus x. It's supposed to be x minus a. Ah, because here the sum will be summation of nc0 x power n minus r and a power r, and that's why this thing. But they should have told us this. I mean, we could have written this as a plus x, right? But they give x as the variable most likely, but then they want the odd terms of this expansion, not the expansion of a plus x power n. Okay, then this might make sense, but yeah, this terminology. Okay. So first question done. Let's go to the, this was just a proof question, so that's done. Wait, actually it's two part, right? So A done, B. So 4PQ is equal to this. So once again, now I'm going to write the equations correctly. P is equal to x plus A. Sorry, it's the odd terms. Yes. So of the odd terms that are the even coefficient terms, that should be P. Yes, so it's going to be x plus a to the power of n, and then you got minus, so even coefficient terms should be plus x minus a power n, and this thing upon 2, and then q is x plus a power n minus x minus a power n, that thing upon 2. So what they want is pq, so this times that. Well, yeah, it's going to be squared and all that stuff. So no problem, 4pq is this thing, obvious. Next, find the value of n if this thing is a naught plus a1 x, okay, whatever. Do you want to find the value of n such that this happens? So it's a polynomial in x and not square root of 4x plus 1. Right, cool. So this thing, yeah, I mean, you can just take 2 power n out, right? So you can see only the x terms are here, and then you got 1 upon square root. Okay. Okay, now I see what's supposed to happen. So it's supposed to be polynomial and not containing these radical terms. And that's why only the odd terms over here should survive, which honestly does happen like that already. So it's just 1 upon 2 power n, and then you got square root of 4x plus 1. Oh, they gave us this little thing over here. So it's 4x, so it's like x power 5, huh? That's how you need to find what n is. Right. So now it just will be summation of like 2 times the summation of. So because it's subtraction, it will be r is equal to odd. So r should be odd, only then it will just cancel. And then you got square root of 4x plus 1 to the power of r. Yeah, and till n, of course. So, right. So what should this be such that we get to the power of 5? Um, the last term over here, that will give us the highest power of x, right? Yes, and that highest power should be 5. So that means square root of 4x plus 1 to the power of 10. That should be this thing, right? So that means the last term will have r is equal to 11. All right. If it's r is equal to 11, then r can be 11 or it can be 12. So that's ambiguous. Oh yeah, I mean it could be 11 or 12. Oh, we got an a naught over here, but only odd terms should work. And okay. Nah, it should be like that because you got this one things coming out, and that's why this happens. But yeah, the thing is x power 5. That means it's gotta have either it should be either 11 or n should be 11 or 12. If it's 11, then the last r that you will get will be 10. Sorry, it will be 11, and that's why you just have square root of 4x plus 1, and that times 4x plus 1 to the power of 5, right? Because the square root dissolves 10 into 2, sorry, 10 into 5, and then you divide by square root of 4x plus 1, and that's why this cancels, and you just get 4x plus 1 power 5. That gives us x power 5, right? Which is the highest power. So all of the other terms, they will give like x power 4 or x power 3 or something like that. X power 5 is obtained from there. So 11 works, and what about 12? Well, yeah, 12 also works. I mean, the 12th, so r is equal to 12th term, right? That thing cancels, and that's why you still get what you should get. Nice. Now what do I do? Should I put 11 or 12? Just put both of them, They didn't give us any values, so might as well put both of them. 11 or 12. Okay, let's go to third. Find the term independent of x in the expansion of this whole thing. So the power of 8, huh? You got, so like x power 3 times of n minus r minus 5r. That will be the power of x, right? This whole thing for the general term. Sorry, it should be 1 upon 3. Right, and this has to be 0 if it has to be independent of x. So that just leaves us with 5n minus 5r is equal to 3r. That means r is equal to 5n upon 8. Yeah. Now n is 8 in this case, so r is equal to 5 should be the term. Just put that in there. This will be n, which is 8c5. Then you got 1 upon 2 cube root of x. Well, just get rid of these x things because they are going to be, gone anyway. So just 1 upon 2 to the power of n minus r, which is equal to 5, like 3. That's it. That's the whole thing. You got 1 over here as the, yeah. So this is the thing. So 8c5 is the same thing as 8c3. Just got 8 into 7 into 6, and then upon 3 into 2, which is like 6. So this cancels. And then that upon 2 power 3, so 8. 7. 7 is the answer. The coefficient. But it's also the term itself because there's no x, so 7. Okay, let's go to fourth. Am I over explaining everything? Maybe. Find the coefficient of x squared. Sorry, what? X cubed. In the expansion of this whole thing. So you want x cubed, huh? Ooh. So you could maybe have 1 times of x cubed or x times of x squared or x squared times of x. right? That's the way to get it. And this is to the power of 9. That's quite a lot. So this is going to be 1 times the x power 3 term from this thing, right? And then 1 times of x power 2 term from this thing, and then wait, but this always increments by 3 in fact. Oh yeah. So well, think about it. It starts off at r is equal to 0, and that's going to be completely just x power 2 times 9, so 18. So the powers of x, those go like this: 18, 15, and then so on. So just multiples of 3. So in the end, you can get x cube somehow. You can get x power 6. You can also just get x power 0, so 1. And then it keeps on going. It's like negative 3 or whatever. Or it should, sorry, it should be 0. Power is 0. Term is 1. Not, I mean, actually, yeah, the x power 0 thing is 1, but then these numbers make it different. And then you got negative 3 and so on. So these things we don't have to worry about because, yeah, it's like this. So 0 times any of these things is when it's futile, and 3 times 1, that's the only, so 3 plus 1. Oh, sorry, 3 plus 0. 1 is just x power 0. That's the only way to get an x cube term, right? So basically just r is equal to 3 term from here, and that times 1, that should do it. So what's the r equal to 3 term from here? Well, that will be nc3 2 power 6, and then you got negative 1 upon 3 power 3. This is the coefficient, and then you got x power 3 automatically. So that should do it, right? I mean, as you go on, your powers decrease by 3 because you get rid of this x square every step, and you put 1 upon x. So basically, you're just dividing by x cube, right? For the x power thing, not talking about the coefficients. So this is the thing. This is the coefficient of x cube term in this expansion. That should do it. So 9c3 2 power 6 negative 1 upon 3 power 3 is negative. Yeah, it's supposed to be negative. 9c3 is 9 into 8 into 7 upon 6. So that will be 3 into 8 into 7 upon 2. So 3 into 4 into 7. We'll just wait a second. And now 2 power 6. That's how it's supposed to be, right? Yeah. And 2 power 6. Who in the right mind would do that? We could just get rid of this 4 in there. So 2 power 8. And then divide by 3 power 3. So this is going to be 3 power 2 right there. No, don't get surprised. It's got 1 upon 3 over here. So this is, yeah, this is pretty normal. So 2 power 8 into 7 upon, well, 9. 2 power 8 is, so this is like 256, I think, right? So 2 power 4 is 16, I think, squared. 256 into 7. 1792.9, negative, of course. So negative 1792.9, that's the thing. Let's go to fifth. Am I taking too long? Maybe. But I just excuse myself by saying and explaining as well. Okay, let's go to fifth. Prove that the coefficient of x power n in the expansion of this thing, okay, is negative 1 power n, and then you got 1 plus x. Okay, fine. So x power n, right? Okay. Wait. I mean, this is going to be an n degree. Okay, so I got it. The x power n term from here, that times 1, and then the x power n minus 1 term from here, and that times x. So this is a no-brainer really, because the nth, so n x power n term is just going to have negative 1 power n. That's the coefficient, just literally that, nothing else. And then it's like nc n minus 1, which just gives us n anyway. So it's going to be plus negative 1 power n minus 1, and then you got n, right? And of course this times of yeah, this is going to be the thing. This will be our coefficient. Okay, so negative 1 power n common, slightly 1, and then you got negative 1 power negative 2, which is 1. So sorry, no, negative 1 power negative 1, sorry, which is supposed to be negative 1. So negative n. There we go. Negative 1 power n, and that times 1 minus n. So this is just a proof question. It's done. So the sixth, prove that the coefficient of x power 4 in the expansion of this whole thing is this, yeah. So it's nc4 plus nc2 plus nc1 times nc2. Okay. You know, there's another better way of doing it by writing as x power 4 minus 1 and that upon all that's right. That's the better way of doing it. But okay, let's do it the normal way. So you want x power 4 coefficient. So clearly x cubed should not have squares on it or something. So you can only have, let's try to write it down. This should be like nc0. That works, right? Yeah, so only 1 plus x squared, that to the power of n minus 1, and then nc0 is just 1, and then plus n times of x cubed times, oh sorry, so n completely, right? Not n minus 1. You got 1 plus x squared, and then here you have n minus 1. Now the thing is that the further terms will contain x power 6 and higher powers. So you can just completely ignore all of that. I mean, you can also do this using multinomial coefficient, but whatever. Just do it using this thing, right? And now it's the question of asking what's x power 4 in this. So x power plus x squared power of n. Yeah, so you can break this apart as well. You can write this as 1 plus x power n plus n x squared into 1 plus x power n, and then you need another term, so it's going to be n into nc1, yes, n into n minus 1, start as nc1 actually, nc1, and then you got x power 4 into 1 plus x power n minus 2. So here we are assuming n is bigger than 2 or whatever. So like this thing, this whole thing, it just gives 1 as the coefficient of x power 0. So right, you can just ignore all of that. Over here just get nc4 as the x power 4's coefficient, and then plus, this is actually just nc1, sorry, yeah, it's supposed to be nc2 in that case, sorry, it should be 2, I just, yeah, nc1, and then x squared term from this expansion, that's supposed to be times nc2, okay, plus nc2. So that's from there, and then from this guy I just want, well, x power 1, right? Yes. So in fact you can just use multinomial coefficient at this point. So it's like 1 power something, x power something, x squared power something. Of course you not have x power anything other than 0, of course. So that's gone, and then I mean, okay, if that's the case, we can just remove this x squared and not think about it, because all of the powers of that guy will just be bothering. And yeah, in that case, just want n minus 1 c1 as the thing, right? So it's supposed to be, well, n minus 1 factorial upon, you got 0 factorial because x squared should not, just put that in so that I can show you what I'm trying to do. So you don't want x squared terms, you do want x terms, right? So because there's no x squared, the only way of having x power 1 is through this x. So it's going to be 1 factorial, and then you got, well, the remaining stuff, so n minus 2 factorial, like that. So this is just n minus 1 c1, right? Yes. Cool. And yeah, now what do we do? What we want to prove is that this thing, so the coefficient of x power 4, oh well, this times n, sorry, I should have done that. This whole thing times n, or instead of saying n, let's just say nc1. Yeah. Okay. Okay, now what we want to prove is that this is just nc4 plus nc2 plus nc1. Wait, what? Where did this thing go? Why do you just not think about this happening? No, I mean, I just disproved that what you are saying is incorrect, because you just consider these 3 terms, you don't consider this term. Why? This is not supposed to happen. I mean, if it was just 1 plus x squared, and it would have made perfect sense, but this, not really. Okay, come on, think. So NC1 term from this expansion just gives us, well, NC1 and then times x squared and then 1 plus x power n minus 1. Okay, that's where we went wrong. So this has to be n minus 1 C2. Okay, that makes sense. So look at this guy, n minus 1 C2 and n minus 1 C1. What does the combination of these give us? Yes, NC2, right? Because of that little thing that we proved, right? That Pascal's identity thing. And that's why it just becomes NC4 plus NC1, NC2 plus NC2. Yes, so this is actually correct. I forgot this is supposed to be n minus 1, right? So since it's also a proof question, it's done. Let's go to 7th now. Prove that the coefficient of x, what? R plus 1 power, sorry, R plus 1th term in the expansion of this 1 plus x power n minus, so n plus 1 is equal to the sum of the coefficient of R power, what am I doing? Of rth and R plus 1th term in the expansion of 1 plus x power. Come on, are you serious? It's just n plus 1 CR plus 1 is equal to NCR plus NCR plus 1, which we already proved. What? We already proved that, right? Just Pascal's identity. So this is done. And yeah, 8. Prove that there will be no term containing x power 2r in the expansion of this guy if n minus 2r is positive but not a multiple of 3. So n minus 2r is a multiple of what? Positive but not a multiple of. So x power 2r, you want that. Okay, it's got n minus 3 right there. It's positive but not a multiple of 3. How would you get this thing? So no term containing it. Well, that's different because this is a positive right there, and then cancellation of terms is not going to happen. So really what we are saying is that, okay, this just won't occur ever, right? That means, so the general term containing x power 2r, it just won't be there. That is, yeah. General term would be like NC, I don't know. They already use what R is, so we'll just use something else. We'll say K. So NCK. You got x power n minus k, or it should be n minus 3 over here because that's what, yeah, n minus 3. N minus 3 minus k. And then you got x, sorry, 1 upon x, right? 1 upon x squared, okay. So 1 upon x squared is 1 of k. What you got, which is basically like n minus 3ck, and then you got x power of, so n minus 3 minus k minus 2k, and that's why x minus, so sorry, n minus 3 minus 3k, right? What you are saying is that this thing, like this power, won't happen if this is somehow equal to 2r. So this cannot be just an even number. That's what you're saying. Huh? So n minus 3 minus 3k cannot be equal to 2r if n minus 2r is not a multiple of 3. So so it's positive but not a multiple of 3. So it's positive, huh? N minus 2r should not be equal to 3 plus 3k. That's what you're saying. If this was somehow equal to 2r, then you would have n minus 2r being equal to 3 plus 3k, right? So just to prove by contradiction, we'll assume that it can happen. That is, for some r, this thing can happen. Then that would just mean that n minus 2r would have to be 3 plus 3k, and of course, like k is just some positive integer or 0, and n minus 2r is positive. It's not a multiple of 3, but look, this is a multiple of 3, so contradiction. It's a multiple of 3 but not at the same time. So yeah, so this cannot happen. 8, we proved it. 9th, if the third, fourth, fifth term in the expansion of x plus k power n are 84, 285, 60 respectively, find the value of x, k, and n. Oh, okay. So wait, what? X also has a, okay. I mean, at this point, it's just terminology, because why would you want to expand something that already has values put into it? But fine, let's just do it. So NC, third term is just got 2 over here, and then so third term A3 is just this thing. NC2, you got x power n minus 2. Right, I'm not going to make that mistake anymore. Ha ha ha. Yeah. Okay, kind of like this. And then a sub 4, that will be nc3. Then you got x power n minus 3 and a power 3. And yeah, I mean, like these, we already know what this is like, right? Yeah. So this was 84. This was 280. And then finally, you just got nc4, x power n minus 4, a sub, sorry, a power 4, not sub 4. That thing is just 560, right? So now we want to find what x, a, and n is. Fine. nc3 and nc4. So, I mean, this kind of like 3 separate equations, that's just not going to work out. You will have to do something else. Wait, maybe there's like geometry equations somewhere. So 28. Huh. That's a weird number. And so 28 to 560, the jump is of 2, right? Okay, let's just go with the ratios and we'll think about what these actually are later. Right? So nc3, and then you multiply by a divided by x, like this thing, nc3 upon nc2, sorry. This is the jump from here to here, which is like 280 upon 84. Is this really just 84? Wow, that's a really bad number. So 280 upon 84, that's supposed to be 70 upon 21, I think. Oh, it's not that bad actually. 70 upon 21, which is 10 upon 3. So there we go. Okay, and then taking the ratio of these, nc4 upon nc3, that times a upon x, that's going to be 560 upon 280, which is just 2. Cool, just divide this out. So that will be like, yeah, when you divide this, just get nc4 times nc2 upon nc3 squared. That's going to be, so divide this. You just get 2 upon 10 upon 3, which is, well, 6 upon, yeah, 3 upon 5. Okay. Oh, this is going to be really bad. nc4, and you got nc2 and whatnot. And we gotta try to do it. So we need nc4 in terms of nc3 or something. That's a really bad idea. But let's do it. Let's see what we get. Right? Let's see. Maybe this hopefully will give us an obvious answer or something. So what nc4 is n factorial upon n minus 4 factorial, that is 4 factorial, and you got this thing, n factorial upon 2 factorial into n minus 2 factorial, and then upon n factorial, or instead let's not use this, let's write it down normally. So n into n minus 1 into n minus 2, n minus 3, right, all of that upon 4 factorial, and then it's going to be n into n minus 1 upon 2 factorial, and that upon n into n minus 1 into n minus 2 upon 3 factorial, this thing squared, by the way. So you can see this n will cancel. N minus 1, sorry. This n minus 1 will also cancel, squared, right? Yeah. 3 factorial right there. Okay. So you can write that out. So 1 upon 3 factorial times 3 factorial. Well, this will cancel, just get 4. And this will cancel, just get 3 right there. So that goes on top, so it's 3/4. This is like 3/4. It's multiplication, right? Yes. Okay. 3/4 of n minus 2 into n minus 3 upon, so n minus 2 squared is the only thing that's remaining. Oh, okay, that should actually also get cancelled. So one of these will get cancelled. Yeah, that's how it's going to be. Right, so one of these just get cancelled and get rid of that thing. It is n minus 3. And now it's n minus 2 here. That should do it, I guess. Right, and that's equal to 3 upon 5. So it cancels and stuff, and it's got 5/4 of that. So 4n minus 12 is equal to 5n minus 10. So I remember I made a formula when the coefficients are in arithmetic progression, but not when these are in geometric progressions. Well, whatever. I don't think I ever need that formula, right? Okay, this just gives us some. Yeah, it just gives us n is equal to 2. Oh, that's unexpected. N is equal to 2? Really? So 9th, n is equal to 2, huh? Uh, I mean, but this n minus 3 doesn't make sense in that. I mean, like, what? NC4? That cannot be. Something's really wrong. That's all I can say. It's 3n minus what? What was that? Okay, let's 4 times of that, and that's supposed to be. Oh, sorry, that 3 got cancelled. It's 4 over here and 5 over here. Sorry. Okay, this is just really wrong. Sorry. It's got 5 and minus 15 is equal to 4 and minus 8. That's how it should be. No, and that can't be. What is happening? 4 and minus 8 there. Okay, let's go with it. N is equal to, okay, yeah, it's correct. Sorry, n is equal to 7. Makes sense. Yes. So the fourth fifth term can exist for n is equal to 7. So there we go. You got the thing. N is equal to 7, huh? And now we can try to do this thing. So the ratios, those will handle themselves. Oh, actually no, those won't handle themselves by. I mean, the ratio of ratios will handle itself, but the actual ratios won't handle it. So you got 280 upon 84, which was, I mean, what was this? 10 upon 3, yeah. That was, this is the fourth term, supposed to be NC3 upon NC2, and then you got A upon X, because, yeah. So now you can figure out what this ratio should be. Yeah. So 7C3, and then you got 7C2 right there. So it's 7 into 3 into, sorry, what I'm doing, 7 into 6 into 5 upon 3 factorial, that upon 7 into 6 upon 2 factorial. This cancels. Cool. It's got 3 right there. 5 third. That just means 2 is equal to A upon X. Cool. So now we got this thing. That A is equal to 2x. You can finally figure out everything. Huh? So the third term, just NC2. So 7C2. And then you got, where did it go? Yeah, you got A power 2 and X power, and then it's like X power 5 and A power 2. This whole thing is 84. 7C2 is just 7 to 6 upon 2 is supposed to be 21. This is 21, and it's 84. It's 4 over there. But you know that A is just 2x, so this is going to be 4 times of x power 7. X vector x is only 1. That makes perfect sense. X is equal to 1, A is equal to 2, and n is equal to 7. That's our final answer. Just write it down. So you want to find what? X, A, and n. Yeah. X is 1, A is 2, n is 7. This was long. Next. Nth. If A, B, C are 3 consecutive terms in the expansion of 1 plus x power n, then find n. 3 consecutive terms in the expansion of, come on. Seriously. It's that kind of thing. I mean, if you were AP, you could probably do that. It's not. Okay, so A is just, wait. Let me think. All it's saying is that these are just consecutive terms. Saying nothing else, huh? Wait, how does this make sense? Okay. Just from ABC, how can you figure out everything? You don't even know what R is. Okay, just think about it. A is equal to NCR, that times, we'll just go with R minus 1. That might be better. No, go with R. X power R. B is equal to NCR plus 1, X power R plus 1, and then C is equal to NCR plus 2, X power R plus 2. And from that, you want to figure out what X is. What? You want to figure out? N. Okay. Sorry. So yeah, let's do that thing that we did, right? Once again, what we'll do is just figure out what E squared upon AC is. because that's the only thing that can cancel these really bad x terms over here. So that, I mean, yes. So x things are just gone. It's just NCR. I'll just go the opposite way. AC upon b square as we did the previous time, right? So it's gonna be NCR upon NCR plus 1, that times of NCR plus 2 upon NCR plus 1. And at this point, let's figure out the formula for this kind of thing. So NCR plus 1 upon NCR, right? You can figure out a formula for that because this comes out everywhere. Okay, it's got n factorial upon, that's gonna be cancelled anyway, right? Just do it. R plus 1 factorial, you got n minus r minus 1 factorial. You also have what? You got n factorial, r factorial, and then you got n minus r factorial. So this cancels, just get r plus 1 right there. N cancels, yeah, n factorial cancels. And you got, this is 1 less than that. So this cancels, you get this. It's gonna be n minus r. Bad handwriting, I know, but deal with it. R plus 1. Yeah, that should do it. That's the thing. That's this thing. Yeah. I'll use this a lot, I guess. Because it came in 2 questions, it might come in more questions. So this is the reciprocal of that thing. R plus 1 upon n minus r. And this is, well, the same thing, just you put r, instead of r, just put r plus 1. So this will be n minus r minus 1 upon r plus 2. Right. This is not helping. Okay. We don't know what r is yet. So then how can you figure out anything from here? Find n. 3 consecutive terms in this expansion. Right. But now what? Without knowing what r is, we don't know anything. This equation won't give us anything. Right. Think. No, it's seriously not doing anything for us. Without knowing R, okay. What else can you do for it? I don't know. 10th is just really weird because without knowing what R is, it's kind of impossible to do this just from knowing ABC. What about these x power r things? If this was just like coefficients, it would be maybe doable, but this thing, it just makes it horrible. Figure out what r is. Wow, as if so easy to do, huh? No, just don't know how to do it. You could try solving this equation and simplifying it, but in the end, without r, it's impossible. And well, we don't know what x is, so that's another problem. Maybe just we know what x is and what we don't know what r is. So you could use some other equations that involve x. But can we assume that we know x? Maybe. I mean, what other choice do we have? Just assume we know x. So then let's get rid of all of this. And then just gonna divide because don't want that r right there. Yeah. This will be basically NCR plus 1 upon NCR, that's just B upon A. So B upon A times, yeah, just don't want that X or R. So you got B upon A times X, and then this whole thing is this, and minus R upon R plus 1. That is equal to, wait, what? Sorry. I put this in very bad shape. Okay, this is it's supposed to be x times n minus r upon r plus 1. That's equal to this, guys. So you can just do 1 upon x right there. And similarly, like c upon b and then 1 upon x, that's going to be, just put, instead of r, just put r plus 1. So it's going to be n minus r minus 1 upon Yeah, you could do that, right? So r plus 2. Now think, this is like two equations and two variables, so it's solvable at least. Yeah, yeah, that is solvable. Okay, now what do we do after this? Let's say that, okay, b upon ax, will call this thing as, I don't know, capital A, and c upon bx will call this capital P. So then this will just be, yeah, these two equations will be different now. This will be n as r is equal to capital A times r plus 1, and yeah, p times of all of that stuff, p plus r plus 2, yes. At this point, let's just say r plus 1 is, I don't know, n, right? Yeah. Okay, no, let's not do it. We still got an n minus r over here, so it's not all that useful. Or is it? Uh, yeah, no, let's just go with that. So then this will be n minus m, n minus of m minus 1 basically, so n minus m plus 1 is equal to a times of m. And this thing will just be n is equal to, well, b times m plus b, yeah, plus m, yes. So you can, yeah, right. Now you need to figure out what this thing is, what we call it, n. Okay, so let's try to do it. So n is equal to a plus 1 times m plus 1. What is this? This is just really bad. Well, whatever. Then n is also equal to b plus 1 times m, but plus b. So now what we can do is just multiply by these things and subtract, and yeah, you'll get the thing. So multiply b plus 1 over here, a plus 1 over here, subtract, just get b minus a times n is equal to, these are gone now. And then just have b plus 1 minus of a plus 1 times is like ab, and minus of b. Sorry. Okay, so n will just be 1 minus ba upon b minus a. And now time to put back what these were, so b and a. Okay, but this isn't this kind of cheating because you're using x, which, yeah, let's just use this. So there we go. N is equal to, so 1 minus ba. Okay, that's gonna have this thing. So abx squared minus bc. Oh, okay, that is just c upon a x squared, right? Sorry. So 1 minus c upon a x squared, and then, yeah, over here b minus a is just well, c upon bx minus b upon ax, whatever. Oh, it's gonna be tough, huh? So we'll have to multiply by a bx squared anyway. So n is equal to abx squared minus, so ax squared is, it's related, it's bc, and that upon, so abx squared, and it's like bx is gone, just acx minus wait, what? Well, that really is like that, huh? B squared x squared. Wow, that was good. So no, okay, that x is not supposed to be there. Sorry, just ac minus b squared. Or is it supposed to be there? I think it's supposed to be there. Yes, it's just x like that. Yeah, that's how it should be. So now we got the thing. We got the expression. We can delete everything else. Just write that in there. So n is just, I mean, why do they want us to do this though? So abx squared minus bc, so just take b common, ax squared minus c, and that upon, so you can take x common, the ac minus b squared, whatever this thing is. So that's done. Let's go to 11th now. if these are any four consecutive coefficients, okay, prove that these things are in AP, huh? A1, A2, A3, A4 consecutive coefficients in the expansion of this guy. Prove that, so A1 upon A1 plus A2. Wait, you know what? A1, right, so A1 plus A2 can be, so this is something like NC, so just take a general term of this thing, it's going to be NCR upon NCR plus NCR plus 1, right? Which, if you recall, this is NCR upon N plus 1 CR plus 1. Okay, fine. So let's figure out what this is supposed to be. N factorial upon N minus R factorial that upon N plus 1 factorial upon the same thing, N minus R factorial. Then you got R plus 1 factorial. So this cancels. This got R plus 1 over here. This, yeah, have that. And then this is gone. Wow. So it's reciprocal of N plus 1 upon R plus 1. So it's like R plus 1 upon N plus 1. That's what this thing is. R plus 1 upon N plus 1. Now N plus 1 is constant over here because we throughout this series. So it's just R plus 1, and R plus 1 is like, yeah, come on. That kind of thing is increasing by 1 all of the time. And so this thing is increased by 1 upon N plus 1 all of the time. So yes, these are in AP. Oh yeah, just put this over here. Okay, let's just put another formula right here, you know. So N plus 1 CR plus 1 upon NCR. Right. Or in fact, even better, just okay, let's just do this thing. This will be R, sorry, reciprocal of this thing. N plus 1 upon R plus 1. Cool, isn't it? Okay, nice. So this is also done. So to 12th. If the coefficient of 5th, 6th, 7th term in the expansion of these are in AP, find the value of N. Right, the coefficients are in wait, okay, I made a formula for, but now I forgot the formula, so let's just do the normal way. R in AP, find the value of N, yeah, whatever. So but yeah, what that means is 2 times of NC5 is equal to NC4 plus NC 6, right? So we can just divide by NC5. So this will be 2 is equal to NC4 upon NC5. You can use this formula for that. So over here R will be okay, so once again, just think about it, how it will be. N minus the smaller number upon the bigger number. Yeah, that's a better way of thinking about it. So if it's NC bigger number upon NC smaller number, we can do N minus the smaller number upon the bigger number. Now this thing is the reciprocal of that. So this will be N minus the smaller number is like N minus 4. And you know, also the numerator will just have the bigger number, that's 5. Right? Yeah, right. Plus, so NC6 upon NC5. So that will be N minus the smaller number, N minus 5 upon 12, 6. That should do it. I made a formula for this, now I don't have it. Anyway, just cross multiply and get the thing done. So this will be, wow, this is really bad. Okay, let's send that there. So 5 upon N minus 4 is equal to 2 minus of this, yeah. So 12 minus that guy, it's going to be 17. But in fact, let's just pull this 2 right here. So this will be plus, and now this will be N minus of 17 upon well 6, right? Yeah, that should be thing is equal to 0. So cross multiply now, finally just get 30 plus N squared minus 21N plus 24. Then you got plus 4, 28 is like 68 is equal to 0. So N squared minus 21N and plus 98 is equal to 0. So 98, well, write 21. 98 is actually prime factorized. So 98 is equal to 4 times of 2 and oh, I think it's not doable. Sorry. Oh, it's like 49 times 2. So this thing is odd number. So put that 2 aside and just, of course, you can do it like that. N minus of 14 into N minus of 7, because I mean 2 into 7 to 7. So 2 into 7 into 7 makes sense, right? Equal to 0. So n is equal to 7 or 14. Now, which of these makes sense? Seventh term cannot be if n is equal to 7 because that will be the. No, it actually can be. There's going to be 8 terms, so it's also correct. So you got two values for this, huh? Huh. Yeah, whatever. Both of them must be correct because in that formula as well, I remember we just used to get two values. So this should be correct. Okay, so what was the 7 and 14? Yeah. Let's go to 13th now. If in the binomial expansion of this guy, the coefficient of 14, 15, 16 terms are in AP, find n. Ah, yeah, the same old, same old. Should I made a formula right away? Damn it. Let's just do it once again. Let's make a formula. So, how do I want this to be? Let's just say if NCR, so our formula will be if NCR minus 1, NCR and NCR plus 1 in AP, then what should be the condition for N, right? That thing. So yeah, what we just have is 2 is equal to NCR plus 1 upon NCR, which is, so it is N minus the smaller number, N minus R upon the bigger number, N R plus 1, plus, well, NCR minus 1 upon NCR. So we got denominator, got N minus the smaller number, N minus R minus 1, so N minus R plus 1. Numerator, you got the bigger number, which is R. That should be doing it. Yeah. Yes, that should be good, I guess. What if it was like R plus 1 or something? No, just do it, right? This will be what? R upon N minus R plus 1, okay, plus, so this minus 2 times of that, so it's supposed to be N minus of 2R, sorry, 3R minus 2 upon R plus 1 is equal to 0. So you got R squared plus R, and then you got this is so really bad, N squared plus, so you got negative 3R minus 2 and then minus R plus 1, so you got negative 4R basically minus 1, and that times of, yeah, that's how it's gonna be N, and then you got plus, so negative all that stuff. It's like 3R plus 2 and then you got R minus 1, whatever that multiplication is, that's equal to 0. So what is this? N squared minus of 4R plus 1 times N. I gotta multiply all that stuff. 3R squared, 2R minus 3R is just minus R minus 2, and then you got this guy, R squared plus R right there. This cancels hopefully. I mean, that was at least good. So 4R squared minus 2 is what this thing is. So what 4R squared minus 2, huh? It's equal to 0. Cool. Maybe you should just need to do that. I mean, okay, let's not go that way. Let's put 4R squared minus 2 over here. And now, first use the quadratic formula. So first of all, find a discriminant. So square root of this guy, it's like 16R squared minus, sorry, 2. Okay, 2 times, so 8R plus 1, and then minus 4 times of this guy. So minus 16R squared. This is nice, right? This cancels out somehow. Minus 16R squared plus 8 cancels. Cool. Just got 8R plus 9, right? That's our discriminant. So the whole thing will just be 4R plus 1 plus minus the discriminant, like square root of 8R plus 9 or whatever. Looks good? I guess so. Yeah. Upon 2, right? So let's see if this works. What happens when you put R is equal? So the last example had the middle terms R as 5. So just gotta put 5 in there. That will be, also like the middle term is in fact the R plus 1 term. So, oh, this is like if T, right, that's the formula that I got, right? Yeah, if these are in AP, fine. So just put 5 in there. It's gonna be what? 20 plus 1, 21 plus minus square root of, so 5 is like 49. Wow, 49, huh? Square. So 21 plus minus 7 basically. So one thing would be 21 plus 7, which is 28. 28 upon 2 is 14 as we got. And another thing would be 21 minus 7, which is 14, and upon 2 is 7. Yeah, so this is the thing. This is the formula. Just put in numbers, churn out the values. Perfect. That's how it should be. Okay, then you finally got this thing. So i.e. these in AP, then n is equal to, okay, let's remember what it was. 4r plus 1, yeah, because 21, right? Plus minus square root of, so 8r plus 9, right? 49. That one too, okay, now I can see it. Fine. Okay, just remember it, except that I didn't remember it at the very start, so yeah, I should have first revised my notes, but whatever. Now you got to see how this formula was derived at least. If I just use this directly, it would have caused confusion anyway. So, I mean, in the end, I would have to derive it sooner or later. So let's put it, minimize this very much, and let's put it here. Just box this now. Okay, let's go to 13. So 13 is similar question. So 14, r is equal to 14, just put that in there and get the values. So 4 times of 14 is 56, and that plus 1 is 57. 57 plus minus square root of, so 8r plus 9, 8 times of 14, yeah, which is 832 is just 112. 112 plus 9 is 121. Nice, isn't that right? This is 11 basically, and that thing upon 2, yeah, of course. That's how it's gonna be. So one thing would be, well, 68 upon 2, I guess. So that's gonna be 34. And another thing would be so minus 11, that's gonna be 40, 46, and that amount is 23. So 23 and 34. This was fast, right? Instead of doing the whole thing, that would have given us errors as well. I don't know. So this was much faster. Next, 14th, determine the value of, how long is this? Oh god, this is really long. Okay, let's keep going. 14th, determine the value of x for which the sixth term in this guy is 1. This is just really, so this one of 7. What's this, log base 2? It's oh come on, where is it going now? Okay, now this, no, please, that's not what I wanted to do. Let's just go to read mode. I cannot move now. Whatever, let's go back. Okay, so this was 14th. Yeah, this is not good. Okay, determine the value of x for which the sixth term in this expansion is 7. So basically like 7c6 and whatever this thing is. Let's just do it. We got 7c6, this is 7c1, right? 2 power log base, come on, log base 2, just put that in. Fine. Just simplify this first of all. So the square root of 9 power x minus 1 plus 7 and then 1 upon. So this is like log base 2 and whatever. It's going to be 1/5 power. So the 5th root of 3 power x minus 1 and that plus 1. So the sixth term in this expansion is going to be 7c1 basically. I know 6, it should be 6, but 1 here. Then this will be to the power of 6 and no, to the power of 1. This will be the power of 6. Yes. So 9 power x minus 1 plus 7 to the power of 1, yeah. And then, oh, it should be 1 upon 2 square root, right? Then you got 3 power x minus 1 plus 1, that is power of 1 upon 5, but yeah. 6 upon 5, sorry. 6 upon 5. And this thing is somehow 84, right? And then 7c was like 7, so it's going to be 1, like 12, okay, cool. Wow. This is just bad. It's got 5th power and whatnot. Okay. I mean, you could just guess a value. That's one thing. Uh, plus 7 right there, what not? It really is like 1/5. What? Why? Should we just guess a value? What other choice do we have? Or you could raise to the power of 10, and that would just make it like really bad to do. Okay, don't do that. Just guess. Uh, so I'm guessing something that gives this as a power of 5 and this as a square somehow. So 9 power x minus 1. Or you can just say 3 power x minus 1 is like a or something. And if x is an integer, it's going to be some power of 3 or something. Okay, so so 3 could work maybe. It's like 3 plus 1. No, it's not a fifth power. 9 plus 1 doesn't work. 27 plus 1, 28. No. 81 plus 1, 82 doesn't work. What? Why is this happening? Uh, are we on the right track? You must be. What else could be the thing? The power of 1 upon 5, and this should give us 12 somehow. Okay, how? Oh, sorry, sixth term. It's got to be r is equal to 5. Oh, that's where everything went wrong. Sorry, 7c2. Okay, this is all just wrong. So you got 7c2 right there, and then this is going to be 2 and 5. Okay, this is how it's going to be. 7c2 is just 7 to 6 upon, well, 2. So this is 21. 21, yeah. 84, there we go. So this is 4. So just a plus 7 upon a plus 1 is equal to 4. That is just, oh, really. Fine, no big deal. Like a is equal to 1 works, just guess a value. A is equal to 1, 8 upon 2, 4. Yeah. And that's the only value, linear equation, right? So equal to 1, and then you got 3 power of x minus 1 as a. That's what we said, right? So 3 power x minus 1 is equal to 1. X minus 1 should be 0. So x is equal to 1. That's it. So x is equal to 1. 14th done, let's go to 15th. Okay. 15th is find the coefficient 1 into 7 in supposed to be x power 7, I guess, in ax squared plus 1 upon bx to the power of 11, right? So no big deal. It's gonna be what? So 2 times of n minus r, so 22 minus of, well, 2r, and then minus of r once again, so 3r is equal to 0. That makes no sense. That makes no sense because, yeah. Oh well, this is bad. Right, because it's not making any sense. That means this is actually not here. So x power 7 won't be there. Let's check. The highest power will be 22, and then it's going down by 3 all of the times. It's going to be 22, and then you got 18. No, not 18. 19. Then you got 16. Yeah, all that stuff like 16 and so on. Just subtract multiples of 3. So in the end, you just get like 10, and then oh, it should be there. Sorry, it should be there. Why is it not? Oh, sorry, it's not 0. It's 7. What am I doing? It's 7. 3 minus 7 is just 15. 15 is equal to 3r. R should be equal to 5. There you go. So r is equal to 5. That means it's going to be 11c5, and then you got a power of 11 minus 5 is just 6. Then b power 1 upon b power 5. Oh yeah, I'll just leave it like that because, yeah. So 1 is just 11c5 and a power 6 upon b power 5, and 2 is, so now in second you want x power negative 7 in this thing. So same kind of thing. I mean, it's got x and x squared right there. Now it's going to be different. It's just 11 minus of minus r minus 2r, so minus 3r is equal to negative 7. 18 is equal to 3r. R should be 6. So R equal to 6 is like 11c6, which is also 11c5. Yeah, 11c5. And this is to be expected because just switch the thing, so cool. Huh, that's weird. Okay, and you got a power 5, and then negative 1 upon b to the power of 5, so it's supposed to be negative. B power, sorry, 6, come on, this is wrong, upon b power 6, just like that, because, of course, yeah, that's how it should be, right? Yeah, that's how it should be. That is r equal to 5, this gives r equal to 6. That's 2r right there. Yes, that's the thing. So it's just negative 7, and that means 18 is equal to 3r, r is equal to 6, and this should work. So 11c5, and then you got a power 5 upon b power 6. And what do you want? Find the relations between a and b so that these coefficients are equal. I mean, these things are already equal. So for that to happen, a and b should be equal. That's it. So third is just a is equal to b, or okay, not necessarily. It's just that a power 6 upon b power 5 is equal to this guy's, like a power. Okay, yeah, it it has to be just that. A is equal to b. Yeah. Okay. So to 16th now. Find the term independent of x in the expansion of square root of x upon 3 plus square root of 3 upon 2x squared to the power of 10. So the term independent of x in this expansion. These are just so repetitive. So we got 1 upon 2, 5 minus 1 upon 2r minus 2r is equal to, so independent of x, it just means x power 0. And that just means 5 is equal to, so 2 plus 1 upon 2 is just 5 upon 2, I guess. So yeah, 1 to r, so r is just 2. Putting that there, just get 10c2, and then you got, well, so 10 minus 2 is just 8, so x upon 3 power 4. So it's going to be 1 upon 3 power 4 right there. And that times, so this quantity to the power of 2, right? Yeah, of 2. And we get this cancelled, and then you just got square 3 upon 2 squared, which is just 3 upon 4. That should do it. Just 3 power 3 right there. So 10c2 is 10 into 9 upon 2, which is 5 to 9. 5 to 9. Just leave it like that. 5 to 9 upon 3 power 3, that times 4, so this cancels with 3. Yeah, it's just 5 upon 12. So we go 5 upon 12. That's A. Let's go to B now. So in this thing and this thing, 1 upon 2 x power 1 upon 3 plus x power negative 1 upon 5 power 8. So yeah, whatever. This got like what? 8 upon 3 is equal to, right now I'm just going to do direct. Okay, it's equal to r upon 3, and then you got plus r upon 5. That should do it. Right. So this is going to be what? 8r upon 15. So r should just be 5. So putting that, let's get 8c5. It's like 8c3 basically. And then you got 1 upon 2 x power 1 upon 3 power 5 basically. So 1 upon 2 power 5. And then the other term doesn't have anything to give. So it's just that. 8c3 is just 8 into 7 into 6 upon 6, which is 8 into 7. So 8 into 7 upon this guy is going to be, well, 7 upon 2 power 2. So 7 upon 4. This is like so lengthy. 17th. Alright, cool. If 1 plus ax power n is equal to this, then find a and n. Serious. Oh, so they just gave us the first 3 coefficients. That's it, right? Fine. So the first coefficient is like 1. That just means a power. Oh, it's not there. Okay, so ax is not there. It's just x power 0. That's why this is justified already. And now 8x. So n times of a, that is 8. And then 24, well, that's just like n into n plus 1 upon 2, that's nc2, and then that times a square, that's equal to 24. So we could just kind of square this, and squared a squared is equal to 64, and then divide this by that. So it's going to be n upon n minus 1, well, 2 times of that actually. Yeah, that is 64 upon 24, which is 8 into 8 upon 8 into 3, so 8 upon 3, there we go. It cancels just with 4 right there. So 3n is equal to 4n minus 8. So n is equal to 8. There we go. That's our answer. So n, we found it, so just put that in here. A should be 1. Yeah, right. So like 8c2, that's just 18 to 7 upon 2, which is, right, 4 into 7 is 20. Hey, wait, what is happening? That shouldn't happen. That, how did it get 24? But, well, that is 8 upon 3, so 3n is equal to, I clearly got n is equal to 8. How did this not work then? Well, 8c2, it's got to be 87 upon, it's not a multiple of 7, by the way. So, why it does not work? No, something just went wrong. That's what I can say. N into 1 upon 2 times a squared, so this guy. N squared, a squared. Okay, let's do it properly. You square that, right? 64. Yeah, that these two equations are just correct. So when you divide, it's get n squared upon n equal to minus 1, so it's going to be n upon n minus 1, but then you divide by 2, so 1 upon 2, it's 2n upon all that stuff. 64 upon 24, that's just 8 into 8 upon 8 into 3, so it's got to be 8 upon 3. That means this is the case. That just means 3n is equal to 4n minus 4. Well, that's giving us something else, n is equal to 4. Of course. Okay, I made some kind of mistake. So n is equal to 4 should be the thing. And now that we have it, a should be equal to 2. So just to double check, what's nc2? So 4c2 is just going to be 4 into 3 upon 2, which is 6. So 6 times of 2 squared, so 6 times of 4 is 24, which is like very correct. So there we go. Okay, let's go to 18th. Find the coefficient of x power, what, 9, y power negative 3 in the expansion of this guy. Okay, x power 9, y power negative 3. I got y over here, but not. Oh, like, it just got x squared on both of these, so it doesn't matter. 0. I can just say it. It's gonna be 0. It's only got even powers of x. Right? No matter what combination of these two terms you get, you will always have x power 2 something plus 2 something else, right? But these somethings are just integers, so it's got to be an even power. But this is an odd power, it makes no sense. And that's why this is just not here. That's how it is. Find the 7th term in the expansion of this guy. So 7 terms with n with r equal to 6, right? Yeah. 10c6, which is like nc4. And you got 3x power, sorry, 3x squared power, because it's 6, it's only 4 over here. You got negative 1/3 to the power of 6. Yeah. Just positive boxes. Same thing, right? So you got 3 power 4 upon 3 power 6 is 1 upon 3 power 2. And you got x power 8. And then 10c4, which is like 10 into 9 into 8 into 7. What am I writing? Upon, well, 4 into 6 basically, because I'll just write this 3 into 2. But this cancels, cool. This becomes 3. So 10 into 3 into 7, that's like 210. So 210, that times x power 6, that upon 9, I guess. So it's going to be 70 upon 3. Should be the thing. Yes. 70 upon 3 x power 6. Huh. This was weird. Wait. Yeah, that's the thing. It's really just the thing. 70 upon 3 x power 6. Let's go to 20 now. Find the term independent of x in the expansion of this quantity. Alright, wait, I've seen this already, right? Look at this guy and look at this guy. These are the same things. Yeah. Okay, so 20 is the same thing as 16, huh? So A basically. 16A and this thing is the same. So 16A is just 5 upon 12. So it's the same thing over here, 5 upon 12. 21 now. 21 is the fourth term of this quantity is okay. Wait, isn't this just the example question that they did? Right? Isn't that the same thing? I don't know. Okay, to the normal way. fourth term. So yeah, the r equal to 3 terms, like nc3, you got px power n minus 3, and then you got 1 upon x power 3. This quantity is just 5 upon 2. So right, nc3 p power n minus 3, and then you got x power n minus 6, that's equal to 5 upon 2. So of course, just I mean, like, this term is not here, there's no x, just x power 0. So n is 6. Yeah, and from there this thing should be you get the idea. 63, that's going to be 6 into 5 into 4 upon, well, 6, so 5 into 4, just 20. 20 p power 3 is 5 upon 2. There we go. So like p power 3 is just, get rid of this thing, 4, it's like 1 upon 8. So p should be 2, sorry, 1 upon 2. So n is 6 and p is 1 upon 2. Okay, next. 22. Both look the same. Sorry, it's going to be p right there. Okay, 22. Find the quotient of x power what? 32, the expansion of this thing. Why do they want me to do this thing? Okay, 15 times 4 is just 60. 60 minus off by 4r minus 3r is like 27 r. So 16 is equal to 7r. There we go. Oh no, sorry. 60 minus 7r is equal to what? 32, right? Yeah, that's the thing. So 7r is equal to, so 60 minus 32 is just 28. R is equal to 4. There we go. So r equal to 4 term. 15c4. And well, okay, these are not there. It's just negative 1 power 4, and that's why that's not here. Yeah, so just 15c4 is the coefficient. That's it, huh? Should I even calculate this? No, just repeat. Or you know what? Okay, let's calculate this. So it's going to be 15 into 14 into 13 into 12 upon 4 into 3 into 2. So this is just 6, and that's why this goes away. Or you could just go with 4 into 3, and that's why this goes. So with this guy, 7 into 15 into 13, which is 30, 13 is like 721, 91. 91 and got 15, so 4, 5, 5, and 0, 91, so got 5, 6, 1, 3, 1, 3, 6, 5, that's the thing. What am I doing? 1, 3, 6, 5. Next question, 23. Write the middle term of this and that. What? Middle term? Oh yeah, so like, okay, I understand what you're saying. So, it's about 12, right? So with 13 terms, you want the middle term. So if there are 13 terms, the middle term will just be the 7th term, right? So 6 terms before it, 6 terms after it, right? So jump from 7 to 6. Sorry, 6 jumps from 7, that's going to be 13. That's why 13 terms. So yeah, I just want the r is equal to 6th term. That's the middle term for this guy. Yeah. There we go, 12c6. 12c6. That's just a lot of calculation. I'm just gonna leave it like that once I'm done. 12c6, y square root of x power 6, and then you got x square root of y power 6. Then you got this guy. Okay, this is just, well, those 5 things cancel. That's really nice. These square root of xy things cancel, but there's square root of y extra and square root of x extra over here. So it's square root of y upon x, and that to the power of 6, so it's going to be y upon x cubed. It's going to leave it like that, because who wants to calculate this? 12c6 got y cubed upon x cubed. That's it. So 23rd is done. First, okay, this 23rd first is done. Okay, second is, so the middle term of this guy. Once again, odd number, just do plus 1 upon 2. Actually, no, wait a second. That was an even number. Oh, okay, okay. So there are going to be 16 terms. So there will be 2 middle terms for this guy. Uh-oh. You will need to find both of them. That's not good. Fine. So the first middle term will be t sub, well, yeah, like t sub 8. And then the next will be t sub 9. Yeah, so, oh, come on. Seriously. T sub 8 and t sub 9. Huh? Fine, so r is equal to 7 and r is equal to 8. Okay, So this r is equal to 7. 15c7. 2x to the power of 15 minus 7 is just 8. So 2 power 8. And then you got like negative. Oh, it's supposed to be x to some power. Okay, that's also there. So x power 8, and then x power negative 7. So it's supposed to be just x power 1. Next one will be 1 upon x, I guess, because x squared is the ratio for just for the powers of x, of course. So we got 2 power 8, and then negative 3 power 7. So it's supposed to be negative of 3 power 7. And then t sub 9 is so 15c 8 for 2 power 7, 3 power 8. And then this is has to have x, this has to have 1 upon x, just x power negative 1. That should do it. So second is this. Just want to leave it like that because let's go to 24. Write the term independent of x in the expansion of this quantity. These are so repetitive. Fine, it's got what, like 20 upon 2 is 10. 10 is equal to r upon 2 plus r upon 3. That's the thing. So like 5r upon 6 or whatever. This is just 2 right here. So r should be 12. If you have it, it's just a piece of cake. R is equal to 12. 20c 12, like 20c 8. Then you got 2x power 1 upon 2 to the power of 8, not 12. That's just 2 power 8. And then you got 1 upon 3 power 12. That negative thing just cancels away. Anyway, just negative 1 power 12. Yeah. So that's the thing. That's the term. Just leave it like that. Don't bother. 2 power 8 upon 3 power 12, right? 2 power 8 upon 3 power 12. There we go. It's 24th. Just like that. Got the answer. Okay, now let's check the, okay, this is not normal solving, is it? Should I check it? Whatever. Let's just solve it as if I'm solving it normally. Okay, so first, oh yeah, second, 11 or 12. They didn't choose 12. Why? I don't understand. Third, T naught is equal to 7. Yeah. This is correct. This is correct. Negative 2 to 4 upon 27. I didn't get that thing. Got something completely different. So fourth was find out x cube in the expansion of this. I might have made some mistakes. That's all I can say. I might have made some mistakes. Anyway, this was wrong. Okay, so fourth was wrong. Ninth directly. Okay, x is equal to 1 is equal to something. Yes. N is this. So you got 2 AC there and not just AC. Why? But b squared. Wait, what? No, something's just wrong. That's all I can say, because we need to have that x in there. This is wrong. That's all I can say, you know. Why? Why? How can you even find something like that? ABC are the consecutive terms in the expansion of 1 plus x power n. Find n. You don't know what r is, you don't know anything. So how am I supposed to figure it out? This one is like consecutive coefficient. It might make sense probably, but like, what is this? And the ratio thing, it changes. So okay. This was what, 9th, right? No, 10th. Oh, let's see. It's got AC. Okay, it looks homogeneous and everything, though I still have my doubts. Why this? You can actually figure out what x should be from there. Just give it another try, maybe. So I'll give it another try. So these are consecutive. What property do consecutive terms hold, really? I don't know. I really just don't know. Come on, think about it, think about it. If if you talk about consecutive binomial coefficients, what property is it that they hold? I don't know. Okay. Oh, I guess you just have to solve that kind of thing. Okay, okay. But then it involves R and everything, so no, no, that's not doable. If I cannot prove this, then there's only one thing I can do, try to disprove it somehow. But if if it was not correct, why would they present it, right? Let's just see if it works for some cases. Uh, so let's go for the simplest kind of case where it's got x plus y squared. Like, yeah. So the terms would then be, so a is equal to 1, b is equal to 2x, and c is equal to x squared. Let's see if this works out. So plug that into here, ac, and or you can see this directly. Look, 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 look. AC, that will have x squared, and then b times of a, that will have x cubed, and then c times of a, that will have, sorry, c times of b, right? That's having x cubed, and then b times of a has x. Like these things, oh come on, these are not even. Let's see what this gives us. So 2ac, that will just be 2x squared, okay, plus b, which is 2x times of a plus is like 1 plus x squared, so got 2x, yeah, like 1, so and then plus x squared, so 2x cubed, and that upon b squared minus ac, so b squared is like 4x squared, that minus of ac, so minus x squared, so got, yeah, 4x squared minus x squared is 3x squared. Look, this makes no sense. Like, how can this be an integer? Why? They should have told us it's like binomial coefficients and not just terms. Let's just change the question. These people. Fine, whatever. I'll give myself a correct because, damn it. Okay, so my formula, if I put, let's say x is equal to 1 in there, what do I get? Okay, that's not the same thing as that. Putting x equal to 1 should have given me the thing. Okay, if x is equal to 1, then this somehow works out. Yes. This just gives us 2. Yeah. And well, in this formula, if I plug these numbers in and put x is equal to 1, I just get, so b will just be 2 and a will be 1 and this will be 1. Uh-oh. That's really bad. But, oh, come on, this is not good. Got a minus b. I must have made some kind of mistake while deriving this. But anyway, I'm gonna give myself a correct because, come on, man, you should have told me you were talking about binomial coefficients. They were talking about terms, literally. Like, look at this. Look at 10th. A, B, C are 3 consecutive terms in the expansion of this thing. Well, there's no way to figure out how n will behave if you know what A, B, C is. I mean, no, you just can't do it. If these are consecutive binomial coefficients, yes, it's doable. You even got a formula for it. But I'll just leave 10th. Fine, because this is obviously not working. Okay, this formula is not working because of course, like we put x is equal to. Oh, come on, it's so weird. A would be 1 and then C would be x squared. So this would give us 0 for some reason. That should not happen, right? Yeah. Huh. Well, man, I don't remember what I did with 10th. So whatever, just leave this 11th. 7 and 12. Well, that's 12. So okay, 11th is a proof question. So this is correct. And then 23 or 24. No, not 24. 34. Right? You had to put r is equal to 14 in there. We even got it very much correctly. So it's like 57 plus minus of 11. So 56. 57 plus 11 will be 60. 8, and 9 upon 2 would be 34. So not 24. Their answer is correct, incorrect, of course. That's it, huh? I mean, this formula worked in this case, so it should work in this case as well. Anyway, I mean, I remember this to be working most of the time. That's most of the time, I mean, all of the time, right? Okay, so this is wrong. That 13th answer is wrong, and my answer is correct. 14th, 1 or 2. Let's see what went wrong. 14th is, so this power like sixth term in this expansion is 84, and from the after what? Oh, that's not like a squared plus 7. Sorry. That must have been what went wrong. So the thing was like a squared plus 7 upon a plus 1. So I just consider this to be a, not a squared plus 7. That's why everything went wrong. That has to be, I think it was 4 or something. I don't remember it is. That was, yeah, I just got 7C 5, right? So 7C5 should be same thing as 7C2, which is 21. So this should have been 4. And that would mean that a squared minus 4a plus 3 is equal to 0. So a would be 1 or 3, but that's not what we got. Sorry, minus 3a and plus 4 is equal to 0. So, no, not 4. That's minus 4, sorry. All of this is wrong. This is just wrong. A squared minus 4a got 7 minus 4. Huh? So a is equal to 1 or 3. Wait, what? So it should not be 2, but it should be 3. But they gave the answer. So it was like what? 14th. They gave the answer as 2. Let's see if 2 actually works. So if x is 2, first of all, just simplify this a bit. We're like, okay, we just know it won't work, right? Yeah. Wait, okay, that's x minus 1 right there. Okay, so a is equal to, right. 3 power x minus 1 is equal to 1 or 3. So, yes, x minus 1 is equal to 0 or 1. So x would be 1 or 2. Okay, that makes sense. Right. So this went wrong. I can understand that. Okay, 15th. 15th, and then this thing. Okay, fine. And then this guy. 11C6 is the same thing as 11C5 anyway. And then a is equal to 1. What? What? Wait, what? A power 6 upon b power 5 is equal to a power 5 upon b power 6. Oh yeah, a is equal to 1. Sorry, this should be a equal to 1. What am I doing? So a is equal to 1 upon b. That would be the thing. So this went wrong, but this was correct. Okay, cool. 16th. 5 upon 12, and then t6 is equal to 7. What? 7. Wait, t was what? And this was which question? 16th. Find the term independent of x in the expansion of this guy. So we had it was what? T. Where did it go? 15th is 15th was different. 16th is t6 is equal to 7, huh? Okay. 16th t6 is equal to, so you want the 6th one, which means 8c5 basically. So 8c5 is like 8c3 basically. So 80 to 76 upon 6, just 80 to 7. And yeah, it's supposed to be like 1 upon 2 power. If it's 6 and it's supposed to be, but it's 5, sorry. Then fine, it's just 3 right there. 1 upon 2 power 3. Yeah, that is in fact 7. Why did I write 7 upon 4? What was I thinking? When I can understand what was I thinking. But it must be 7. So what went wrong? Why did I write 7.4? Oh, I must have done this kind of. Okay, I must have done this 5 and then this 1 power 3. That's what I must have done. That's why I got 7.4. Oh, it's supposed to be power 3 and power 5 because you want the fifth term, right? So r is equal to 5. That kind of. Sorry. Yeah, r is equal to 5 term, the sixth term. That's why 1 power 5 and not 1 upon 2 power 5. Okay, so that's why this went wrong. So B was wrong and this was correct. I'm making unusually hard mistakes today. 17th. So A is equal to 2 and N is equal to 4. That was wrong. Oh, sorry, that was correct. Then 18th is 0. Okay. 19th is 70 upon 3 x power 8. 70 upon 3 I got, but it's for 8. 19th is find the 7th term in the expansion of it's like basically 6 over there. That's why. Oh yeah, it should be x power 4 because sorry x power 8 because yeah x square power 4 and that's why this thing. So why did I write x power 7? X power 6, sorry. I don't know. Huh. That's not supposed to happen. 7th term in the expansion, so the 6th basically. And it's like okay. Okay, I maybe just maybe I put 10 minus 7 3 so x squared to the power of 3. That's what I should have. Yeah, so maybe I did that. I don't know. But it should clearly be x squared power 4. So this also went wrong. Though mostly it was correct. It's just this thing went wrong. So 20. Find the term. Okay, yeah. 20 is 5 upon 12. Okay, that's right. Then 21. P is equal to 1 upon 2 and n is equal to 6. Okay, that's right. 22. 15c4, which is whatever this thing is. So that's right. Then 12c6 y upon x cubed. Okay, that's right. And these two things. So, oh, 23rd has two things, right? That's A and that's B. Okay. So 15c7. Where did negatives go? You gotta have that negative over there, right? So 23rd. Yeah, one of them must be negative at least. I mean, the middle terms, one of them must be negative. You cannot have both being positive, right? Mm. Look at this guy. It's not negative right there. It's got to be like that. So I will say, okay, they put somewhat an incorrect answer, but fine. Makes sense. They just skipped a negative, whatever. 24th, 12 and 8, same stuff. Yeah, this is correct. So in total, I made 1, 2, 3, 4, 5 mistakes in 24 questions. Fine. I don't even know what these. Oh yeah, and then 10th they just yeah. So 10th I will just skip because it's an exceptional case. That was wrong, and this was wrong. This was wrong. So wait, isn't that just 4 questions? One. Oh, that's all it. Actually, yeah. That was just a silly mistake. Fine. 1, 2, 3, 4, 5 mistakes. That's just embarrassing. Fine, fine, fine. Whatever. Then you have this thing greatest binomial coefficient NCR is greatest if r is equal to n upon 2, r is equal to n minus 1 upon 2 or n plus 1 upon 2 if is odd. No, okay. That's just, I mean, for the normal NCR thing, but the actual coefficient thing, that's little different. Why are they explaining this? I mean, they already put questions on this middle term concept, and then they are explaining this. What? Whatever. Greatest term in the expansion. Exactly. This thing, it's kind of important. So let's just read what they are saying. So yeah, I mean, usually what happens is that it starts increasing, and at one point it decreases, right? So if you think about it, it's got like NCR x power r, or it should be like a power n minus r and then x power r, something like that, right? So usually r is just, some kind of what do we say, integer, right? But if somehow your r could be any real number, and then if your NCR was somehow defined like that, then yeah, like this whole thing will get a maxima somewhere in the distribution, and then yeah, so that's why you have a greatest term, not two or three greatest terms. But I've never seen two or three greatest terms. Yeah. Okay. So they are saying, do this thing that whenever it will start to decrease, it will just start to decrease. You just find out where it decreases, and the term just before it decreases, that will be the greatest term. Yeah. So what you want is tr plus 1 upon tr. That thing should be, wait, what are they doing? Yeah, like tr, right, exactly the same thing as I said. So the term before this term is smaller, but then after this term is bigger, right? So it's the term right before the decrease starts happening, and that will be the greatest term. So making these conditions happen, just have tr plus 1 upon tr is bigger than 1. Now that's the same thing as saying ncr plus 1 upon ncr, or it should be r and then r minus 1, sorry. And then you got, so it's x plus a power n. Oh, that's different. Let's just go with 1 plus x power n instead. Yeah, that's better. So just the ratio of the second thing to the first thing. Yes. Right. So this will be like just x because one more, right? So that thing should be less than 1. And nc, oof, it will, I mean, it will actually be bigger than 1, sorry, when or equal to, because tr plus 1 is bigger than tr. So yeah. And then you got nc. So x is just a positive ratio, right? It's not, yeah, numerically greatest term, right? Not thinking about the actual signs or anything. And then you got nc r plus 1 upon ncr. That times x, that should be less than or equal to 1. So when does this happen? That's what we're asking, huh? So first of all, this thing can be written as what was this, n minus of the smaller numbers, r minus 1 minus r plus 1 upon the bigger number, that times x, that should be equal to 1. And then, or you could say it's like equal to 1 upon x maybe, and n minus r upon r plus 1, that's actually be less than or equal to 1 upon x, right? Yeah. And we just need to figure out for what value of r does this actually happen. Yeah. So what are they saying? So r is less than n plus 1 upon 1 plus x upon a. That's the solution of this thing. Let's try to do it. You could just, I mean, multiply, right, on both sides. So that might be the best thing to do. So this will be r upon x over here, and then got r plus 1 upon x over here. This will be like n plus 1 is bigger than or equal to, well, r into 1, so that's like x plus 1 upon x times r, and n is, well, that's not equal to it's just r over here, right? It's gonna be 1 plus x upon x times r, sure, but you got 1 upon x right there. I mean, you could just have multiplied directly or whatever, but whatever. You got the thing, right? So r is less than or equal to x upon x plus 1 times n plus 1. And then r is bigger than or equal to, so just multiply by x on both sides. So it's going to be what? X, so nx minus 1 upon 1 plus x. Okay, so r is bigger than or equal to nx minus 1 upon 1 plus x, and it's less than or equal to, well, x times all that stuff, right? Yeah. But I'm thinking, okay, just divide by 1 upon x. So divide by x, and then let's, instead of going for this, yeah, just take first to second ratio. So we'll just say, I don't know, call this thing mu. That will be the first to second ratio. So so if this is like x plus y power n, okay, that's not what we want to do. A plus x power n, if it's something like that, right? Then mu will just be a upon x. Then you can write this thing as n minus of mu upon 1 plus mu is less than or equal to r is less than or equal to, so this quantity will just become n plus 1 upon mu plus 1. That should do it. Huh? Like that should do it. So yeah, well, that's perfect. Just some integer between these. Now let's think about it. You can write this thing as well, minus 1 and plus 1, so it's going to be what? N upon, sorry, actually you can write this as n plus 1 upon 1 plus mu, and then thing minus 1 is not equal to r is not equal to n plus 1 upon mu plus 1, right? Yeah. So I mean, these quantities, these may or may not be actually integers, so that's problematic. Yeah, sure. But we have this thing happening. Well, think about it. That you can think of like this. So come on, just delete all of it. So we'll think about this inequality first. It will be basically like n plus 1 upon 1 plus mu. That is less than or equal to r plus 1. And then you got this is bigger than or equal to n plus 1 upon mu plus 1, right? So now if, I mean, it should be, sorry, it's less than or equal to r, sorry. It should be bigger than or equal to r. Yeah, exactly. So whenever this happens, yeah, right. So now the question is this like r is this a ceiling function or the floor function? Why not both of them, right? I mean, both of them could work. So r is either the floor function of n plus 1 upon 1 plus mu. Yeah, but actually no, it is in fact just the floor function, because even if it is like somehow equal to r plus 1, even if that happens, right, it will actually, no, okay, it could be the floor function minus 1. Yeah, that's a problematic thing. If this is somehow an integer, then you just need to do minus 1. That's how it's gonna be. Okay. I mean, fine, I guess. If this is not an integer, then you just do that. So greatest term will be something like this. So if, just call it a is equal to n plus 1 upon 1 plus mu, where mu is first upon second, right? If a integer, then r is equal to so yeah, like all of these r's would actually work. Then you just got basically two of these numbers, right? Exactly. So the number less than that will work. At the same time, the next number will also work, right? Yeah. This is somehow an integer, and it's gonna be either r or minus 1 or something like that. Let's just not do that and go by the way they are telling me to do it. right? I mean, doing this inequality, which I kind of don't like, but whatever. So basically, R is between a and a minus 1, where this is of course an integer. R is an integer, right? And you just have to check what values of R will satisfy this inequality, and then check for all of them. This is the greatest term in the expansion thing. Okay, fine. I think we should stop for now, right? Because I mean, this had so many questions, like 24 questions. Whatever, I think we should stop. Yeah, because there are even more questions now. Fine. So let's stop. I'll see you guys in the next video.